Afternoon, everyone. My name is Javier Cañada, and I'm a PhD student at Imperial College London under the supervision of Dr. Ana Ruiz Terán. And today I will be talking about the structural behavior and design criteria of segmental high-speed railway bridges, and more in particular about precast concrete segmental bridges. So these are a type of bridges in which the deck is subdivided in smaller segments, and the segments are joined to each other and stay in place thanks to the forces of pre-stressing. This technology has become very popular in the last decades thanks to its many constructive advantages, which come mainly from the use of precasting and include faster construction, reduced creep, higher quality control, flexibility in alignment, thanks to the division of the deck in short segments, minimization of the false work, and independence of the construction from the environment. All these advantages have led to the construction of many bridges using this technology, but mainly for road and urban or light railway projects. The number of these bridges in high-speed railway lines remains very, very limited. And it is only now starting to grow, with actually a couple of examples in high-speed 2 here in the UK. The reasons behind this low number of precast segmental bridges are the need of large-scale projects for this system to be economically appealing, and some reticence towards change in how high-speed railway bridges are built, due mainly to the lack of knowledge on how the joints affect the dynamic behavior and fatigue of the bridge. And this is because, from a structural point of view, the main characteristic of precast segmental bridges is the presence of unreinforced joints between the segments. If the section decompresses, these joints open to a certain height that depends on the global equilibrium of forces in the bridge. However, the current trend in precast segmental bridges is to include enough external and internal pre-stressing to avoid the opening of the joints even at the ultimate limit state. So in this context, the objectives of my work are studying the behavior of precast concrete segmental bridges under the loads of high-speed trains and proposing a set of design criteria for these bridges, paying special attention to the optimization of the pre-stressing. To be able to do this, I have been developing a numerical model aiming at efficiently reproducing the most important characteristics of these bridges. So now I will develop a bit more on this model and how it has been calibrated based on experimental results from the literature. The existing research on precast concrete segmental bridges already includes several proposals for numerical models that can be classified based on their complexity, from the simplest 1D models using bar and beam elements, such as the one on the slide, to the most complex that use 3D solid elements. One of the most relevant aspects of the models is how the joints are introduced. The joints can be introduced either in a simplified way with a flat surface and friction between the segments, or including the shear keys between them. Also, considering it or not, the friction behavior of the external tendons at the deviators has an impact in the models. In my research, I have chosen to use a 3D model with cell elements, since it allows studying the spatial behavior of the bridges at a reasonable computational cost, which makes it suitable for demanding analysis, such as those concerning the dynamic behavior of bridges for high-speed trains. The model reproduces the most important features of precast segmental bridges, such as the joints, which are modeled flat, and both the internal and external tendons, considering friction at the deviators. One of the critical features is the use of two contact elements in the top slab. The position of these contact elements controls the behavior of the model once the joints have opened. This model has been calibrated using the experimental results obtained by Takebayashi on a full-scale test span that was loaded until failure. This test was made on a road bridge project, but it is one of the very few full-scale load tests that have been made on precast segmental bridges. The results of the finite element model showed very good agreement with the experimental results, both in terms of deflection and opening of the joints. In the figure on the left, we can see the impact of using one or two contact elements at the top slab. And the calibrated model has also been employed to analyze the influence of certain parameters, such as the friction at the deviators, the initial pre-stressing force, the area of the pre-stressing, the friction at the joints, and the use of different material models and element types, including solid elements for the top slab. In order to verify that the modeling strategies can be generalized to other precast segmental bridges, similar models have been created for two segmental beams tested at the Centre d'études du bâtiment et des travaux publics. One of the beams has only external tendons, but the other one incorporates internal tendons, which permits studying the influence of bonded tendons in the model. Once again, the results of these models match very well the experimental results. And these new models, as I said, allow studying the behavior of external and internal pre-stressing, showing that the stresses in internal tendons at the joints grow much faster than in the external tendons. But within the segment, the stresses in the internal tendons remain almost unaffected. Moreover, the influence of using epoxy at the joints was studied with a simplified model and showed a very limited impact in the behavior of the beam, only making the stiffness transition more sudden when the joints open. This is why in the following models, the effect of epoxy has not been included. All these modeling strategies on the previous bridge and beams have been used to create a finite element model of a benchmark case of a precast concrete segmental bridge for high-speed railways. The bridge chosen to inspire this benchmark case is the viaduct of La Bohème in the Southeast Atlantic line in France. This viaduct consists of 10 precast concrete segmental spans that were put in place by the progressive placement method. For the development of the model of the benchmark case, both the cross-section and the profile of the viaduct have been simplified, reducing the number of spans to 3, and the layout of the pre-stressing also had to be adapted to the simplified configuration. So this model for the benchmark case has been first used to study the influence of allowing the opening of the joints under different static load combinations. The original bridge was designed to keep the joints closed under the loads of the ultimate load state. However, allowing the joints to open under the service characteristic combination of loads would allow reducing the pre-stressing by 29%. In this case, also, there will still be a reserving resistance of 2 times the service loads before the failure of the bridge. Moreover, if the joints were allowed to open freely and the ultimate limit state was evaluated at the failure of the bridge, the pre-stressing could be reduced down to 1/3. The current version of the Eurocode, on the other hand, states that at the ultimate limit state, the joints should not open more than half of their height. This is obtained with a pre-stressing that is 73% of that required to keep the joints closed at the ultimate limit state. It must also be taken into account that the loads introduced by a real train are only 1/3 of the characteristic values of the vertical loads used in the design load combinations. So the joints could only open under the passage of trains if the pre-stressing is designed to attain the ultimate limit strength of the bridge at the ultimate limit state. To confirm this point, the behavior of the model has also been studied under the dynamic loads generated by the passage of real trains over the bridge, and this model accounts for both vehicle, rail, and rail structure interaction, and also considers the effect of the irregularities of the track following the model developed by Pring. And the results show that as long as the joints remain closed, the dynamic behavior of the bridge remains almost unaltered, independently of the amount of pre-stressing. Only if the pre-stressing is reduced to a point where the joints open under the loads of real trains, then the dynamic behavior of the bridge is affected, as shown in the change of accelerations in the bridge. Since the amount of pre-stressing controls also the opening of the joints, it affects the redistribution of moments in the bridge. For lower values of the pre-stressing forces, the redistribution of moments with or without joints changes considerably, showing differences of up to 20% at the service limit state. On the other hand,
Javier, we're pretty much out of time. If you could go to
yeah,
your,
I'm almost done. So if the opening of the joint is restrained, then the differences are as low as 1% at the ultimate limit state. And I have also, checked that with only external pre-stressing, the ductility is higher, because if only internal pre-stressing is used, then these internal tendons can fail prematurely. And to conclude, the current design approaches for precast concrete segmental bridges use high pre-stressing forces that allow ensuring that the joints remain closed or almost closed under all load combinations, which permits analyzing these bridges, neglecting the effect of the joints. However, if the joints are allowed to open, it should be possible to reduce considerably the amount of pre-stressing while maintaining a significant reserve of strength, and the dynamic behavior will not be affected if the joints remain closed under the loads of real trains. And finally, as I said, it has been seen that the internal tendons in some cases fail prematurely when the joints open, in comparison with the external tendons. And that's all. Thank you very much for listening to my presentation, and I will be happy to take any questions.
Thank you, Javier. A very interesting presentation, and as I alluded to at the beginning, very topical, because of the increasing number being built in the UK for high speed 2. So I think we've just got time for a couple of questions. So any other fellow judges or audience, please put them in the chat. The question I had was, I suppose, building on the analysis you've done, and then taking a step back and thinking about the longer term. Is there any more you can tell us about how your thoughts about the longer term, let's say, benefits or challenges that could arise with this kind of viaduct construction? I mean, is there a risk of loss of pre-stress? How thoughts around the sort of whole life picture? Is there any more that you're able to tell us about that?
Yes. So, I mean, when I was presenting, I was mainly focusing on the advantages of the precast technology, let's say, but these bridges, when they were starting, they were mainly being built only with external pre-stressing. Nowadays, the trend is to combine both internal and external pre-stressing. And then looking at the full life of the bridges, then it is there where the external pre-stressing actually has some advantages related to the fact that it is easier to inspect, and if it's properly designed and constructed, it can even be replaced if needed during the life of the bridge. So by looking at the effect of combining internal and external pre-stressing, one of the things I want to see is if for high-speed lines, for bridges in high-speed lines, it will be possible to benefit from these advantages of external pre-stressing as well.
Thank you. And in the meantime, we had lots more questions from other judges in the chat. So if I've just got short answers, if you're able to. So Andrew Foster from Covey Bridges asks about the validation of the physical tests against the numerical tests. And so he said, what measures did you take to obtain the agreement between your finite element models and the physical tests?
So, I mean, the physical test is available in the literature, and there are measurements of deflection, the stresses in the tendons, and all sorts of many other variables, and opening of the joints, obviously. And the way that I have calibrated it is I have taken the variables that were given in terms of, let's say, characteristics of the materials or losses of the pre-stressing. I've been as, say, accurate as possible with those values in the model, and then I have seen that those contact elements that I have been talking about in the top slab, they have a big impact on the behavior of the model. So that has been the point in the model where I have been able to play a bit and calibrate the model, because position of that contact element, it is representing at the end of the day, the position of the resultant of compression forces in the concrete. So I can actually estimate it based on the equilibrium of the section, let's say, and obtain the value of the position where that contact element has to be. And I've seen that, assuming that everything is plastified, for example, I reach a good estimation. I reach an estimation that allows me to reproduce quite well the experimental results. I don't know if the question was really in that sense.
I think so. Well, it's good to get that background, and well, both that question and several others in the chat. I'm sure we'll continue them at the breakout rooms at the end of this afternoon. So hopefully you're able to stay on, Javier. I know I'd love to talk to you more about this as well. So thank you very much.